Every headline about orbital simulations assumes a simple truth. If you plug in numbers, physics works. But that assumption hides a brutal failure mode built into the most common algorithm used for decades. When we simulate orbits with explicit Euler, energy does not stay constant. It leaks away or appears from nowhere, causing satellites to spiral out of control within minutes rather than years. This is not a bug you can patch with better code. It is a fundamental geometric lie that breaks the laws of physics at their core. Today, we examine why this specific numerical method fails so catastrophically for orbital mechanics, and how symplectic integrators preserve the very energy conservation that makes spaceflight possible. The problem begins with what explicit Euler assumes about motion between 2 points in time. The algorithm calculates velocity based on current position, then moves the object forward as if it traveled in a perfectly straight line at constant speed for that entire duration. In an orbit where gravity constantly pulls the object sideways and changes its direction every millisecond, this assumption of linear motion is a fatal simplification. Because the method treats each step independently without accounting for how velocity curves over time, it introduces a geometric error that compounds with every single calculation cycle. Consider what happens when you apply this straight-line logic to an orbiting body. The simulation calculates a new position based on current speed, but because gravity has not yet fully turned the object during that time step, the resulting path overshoots where it should be. This overshoot places the satellite slightly further away from the central mass than reality dictates. In physics terms, the algorithm injects artificial energy into the system with every iteration. The orbit does not close. Instead, it spirals outward in a slow but relentless drift that violates the conservation of energy inherent to Hamiltonian systems. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This geometric failure explains why explicit Euler is useless for long-term stability despite its computational simplicity. While one source confirms that game engines like Godot rely on this integrator by default, noting it forces developers to artificially increase tick rates to 60 Hz just to mask instability, the underlying geometry remains flawed. The method assumes straight-line motion between steps and often creates a false sense of security until the simulation explodes or drifts away entirely. To maintain stability for long-term orbital scenarios using explicit Euler requires an impractically small time step that increases latency and computational load far beyond what is necessary with better methods. The trade-off becomes stark when you compare this to symplectic integrators, which are designed specifically to preserve the phase space volume of physical systems. Unlike explicit Euler, these advanced algorithms respect the geometric structure of conservative forces like gravity. They ensure that if a system starts with zero net energy change over a full cycle, it ends with exactly that same state after one period. This preservation means orbits remain stable for thousands or millions of iterations without drifting inward to crash into the planet or outward into deep space due to numerical noise. In production game engines and simulation tools, the reliance on explicit Euler is often a legacy architectural decision rather than a choice based on physical fidelity. Developers are frequently forced to manually tune physics parameters just to prevent explosions in fast-moving objects, because the algorithm cannot naturally handle high velocities without breaking down. This constraint means that every time step must be short enough to keep errors small, which directly conflicts with the need for input responsiveness and low latency in real-time applications. The result is a compromise where simulation accuracy is sacrificed for computational efficiency, leaving engineers constantly fighting against the math rather than working with it. The specific geometric mismatch becomes clear when you visualize the error accumulation over time. In explicit Euler, the velocity vector used to calculate position is updated after the position has already moved based on an outdated velocity value. This lag creates a systematic bias where the object gains energy in each cycle because the algorithm consistently pushes the orbit slightly further out than it should be. While this might seem like a minor deviation for short simulations, over long durations the error grows exponentially, rendering any prediction of future position completely unreliable after just a few orbital periods. Symplectic methods solve this by updating velocity and position in a way that respects the underlying physics symmetries. They do not assume straight-line motion, instead they account for how forces change continuously through the time step. This allows them to take larger steps without losing stability, making simulations both faster and more accurate than their explicit counterparts. The difference is not just academic, it determines whether a simulation can run long enough to be useful or if it fails before the first orbit completes. The industry default of using explicit Euler persists because for general game physics involving collisions and explosions, the geometric errors are often acceptable as long as objects do not fly through walls. However, when the goal is orbital fidelity where energy conservation is paramount, this method is fundamentally broken. The lack of specific benchmark data comparing Euler versus symplectic integrators in real-world orbital scenarios leaves a gap in quantifying exactly how much energy drift occurs before failure. But the theoretical limits are clear. Without a symplectic approach, long-term stability is impossible to achieve with explicit methods alone. This insight reshapes our understanding of why certain simulations feel wrong, even when they look visually correct on screen for short durations. The hidden cost of computational simplicity is a violation of physical law that only reveals itself over time. Engineers who understand this distinction can choose the right tool for the job, avoiding the trap of using a method designed for bouncing balls to simulate planetary motion where every joule matters. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.